x and y in the domain. Hence, thus f of z is equal to u naught plus iv naught for all z and d. Meh? Meh. Let's see here, another thing, little theorem we could prove. This is not a theorem, I call this an example. Suppose you have f of z is sine squared z plus cosine squared z. All right? For z in the complexes, what can you tell me here? Well, then df dz is what? It is 2 sine z cosine z, right? Minus 2 cosine z sine z. How do I know this? I'm thinking Wirtinger Calculus, right? Obviously, the partial derivative with respect to z bar is 0. Consequently, the complex derivative exists, and it's given by the partial derivative with respect to z, which is what I wrote down. But what is that? Zero, okay. So then, thus, f. So, I think I've buried the lead here. I have a theorem which simply says that, theorem 5.38, it says that if f is holomorphic with derivative 0, then f is constant. That's the one I forgot. I'm sorry, guys. I was supposed to tell you this one first. In my excitement about the conformality, I got a little bit off schedule here. So if if f is holomorphic on D, all right, and f prime of z is equal to 0 for all z and d, then f is constant on D. And the proof of theorem 5.38 is almost the same as the proof of the theorem I just gave. See, if the complex derivative is 0, then by the Cauchy-Riemann equations, we get that all of the partial derivatives of f, like all the partial derivatives of u, all the partial derivatives of v are 0. Consequently, the gradients of u and v are 0, which then means that u and v are constant on D. It's essentially the same thing I just went through for the proof of that. Now we can apply it to the example. So we have the derivative is 0. Therefore, that function's constant, right? So f of z is equal to, well, how about f of 0? F of 0 is 1, right? So lo and behold, we have shown that sine squared plus cosine squared for the complex sine and cosine is identically equal to 1 for all z in the complex. Which is a little bit interesting because when we study sine and cosine carefully as complex functions, they're not bounded, right? Like if you look at imaginary inputs, you can get coshas and sinches and such, and those can blow up. So, but nevertheless, the sum of sine squared and cosine squared still conspires to be 1, even though sine and cosine conspire to get huge in various parts of the complex plane. I think it's kind of neat. All right, so moving along here, I think that pretty much exhausts my chapter 5. So that brings us to the realm of my chapter 6, which I think I have not printed out. So I'm going to have to wing it. That's okay, we got 10 minutes. So what's next? A couple different ways to go here. Let me do the thing that has the most sort of connection with what we're doing, which is the inverse function theorem. So do you guys know what the inverse function theorem is? Let me ask the question, let me scale back the question a bit. If you've got a function that goes from the reals to the reals, right? What does it take for the function to be invertible at a point, like close to the point?
It's got to be non-zero. I don't know if that's sufficient.
The function has to be non-zero. I don't think that's true. Has to be identity, no. I mean, something has to be non-zero. Your heart's in the right place, but like, suppose I draw a picture, right? So here's my graph, right? Y equals f of x. Where can I hope to find a local inverse? Let me ask a different question. Where can I be sure I'm not going to be able to find a local inverse? Local inverse means that I take the function, I restrict the domain to an open subset around the point on which the function's invertible, right? So like.
Oh, you mean like there's two different x values that are going to give you f of x?
Right. Yeah. Yeah. So we need one-to-one. Whatever the restriction is, it must be that the set we restrict to, it has to be like one-to-one. Otherwise, when we try to invert it, our inverse function will try to take those two values we map to the same y value to two outputs, which we can't have because the function has to be like single valued. The inverse has to be single valued, you know? So the place where we run across trouble for the horizontal line test, there's 2 points here, right? This one, roughly speaking, and that one, right? Those are the place where if I try to do the horizontal line test, I get into trouble, right? Because I got these two inputs give me the same output. So if I was to try to invert the function there, it wouldn't work, right? So can you tell me in terms of calculus what's the problem here? I mean, we have f prime of, let's say, p naught, p1. F prime of p naught's what? Yeah, 0. And f prime of p1 is 0. So we can't invert a function of one variable, one real variable, at a point where the derivative is 0. Not on both sides of the point, at least. At best, we could invert it like to the left or to the right. Yeah. For example, x squared, f of x equals x squared. You could invert for positive or you could invert for negative, but you can't straddle the origin and find an inverse. Yeah. How does this story go for complex? What do you think? So, did you guys ever think about how you find an inverse function? Has anyone ever showed you? I'm sure they have, right? Like, if you have f of x equal to x minus 1 over, x, and you want to invert it, what do?
Solve for x.
Solve for x, right? We'll set it equal to y and solve for x. That's right. So, that gives us x minus 1 is equal to xy, which gives us x minus xy is equal to 1, which gives us x times 1 minus y equal to 1, which gives us x is equal to 1 over 1 minus y. Lo and behold, that's f inverse of y. Right. So if you think about a complex function, w equals to, say, f of z, right? If we wanted to solve for the inverse function, we want to solve for z, right? So let me give you kind of an approximate argument here. If I had, say, f of a plus f prime of a times z minus a, right? So this is approximately. If I wanted to make that exact, I'd level my f prime of a up to the difference quotient function, right? I could do that. But if I was going to try to find an approximation for the inverse function, I'd just solve that for z. And so if you do that, what do you get? Which gives me z is equal to like a minus, let's say, f of a over f prime of a Oh, my bad. Let me just stick with the w minus f of a. Rats. Yeah, fine. W minus f of a. Sure. Into, yes. Thank you. I think. Hold on a second.
Yeah, it looks like it.
Okay. Now my claim is that like that's approximately, and this is a little bit sketchy what I'm doing, but it's approximately G inverse of W. I mean, my bad, F inverse of W. Right? And so like, if I picture it, I've got A over here in the Z plane, and I've got F of A over here in the W plane, right? So this, to rewrite this a little bit more, this is really like A plus 1 over F prime of A times W minus F of A, right? So what does this suggest about the inverse function? Is it differentiable in the complex sense? If so, what would a complex derivative naturally be understood to be? Like what I see from this is that like, I'll write the other notation, df dw, df inverse dw, it seems like it should be 1 over f prime of a. Yep.
So that shows why it can't be like when you take the derivative and you get like the tangent, that's why it can't be 0.
Right. I think so. It's a little sketchy because I can't draw this picture in complex, right? But I can, to a very good approximation, say that a complex function can be approximated by its so-called linearization, right? Like I said, it's a little bit not quite the Carathéodory, because the Carathéodory puts a function here which actually gives us an equality, right? But if I drop back from that for a second, just to make a formal, sort of a more informal discussion with you guys, well, this is a good approximation for the function, right? And it's still true that, I mean, it just sounds reasonable, doesn't it, that if we find the inverse to the approximation, that should probably be a good approximation to the inverse of the function. It turns out that that's actually not a crazy thought. That can be made rigorous. Not in this class. But anyway, long story short, when I go through the algebra, we just learned that the linearization of the inverse function, or at least its approximation, the derivative of it is 1 over the derivative of the function, right? But this is exactly how the derivative and the derivative of the inverse function work in like calculus 1. I can derive it a little bit more systematically, like I'll do it over here. So if I had, f inverse of f of z, right? If the inverse function exists, then that's equal to z, right? And if there's a chain rule for complex calculus, which, oh yeah, you guys are proving that for me, so yay. So there is in fact a chain rule for complex calculus. Then if I differentiate this composite, what does it give me? It gives me df inverse dz at f of z, all right? Derivative of the outside function evaluated at the inside function times the derivative of the inside function, right, is equal to dz dz. But with dz dz is 1. Which shows you, by the way, more definitive, I mean, without argument, that if a complex function has an inverse function, right? it must be the case that both the derivative of the function and the derivative of the inverse function, they both have to be what?
Non-zero.
Non-zero, right? Yeah, I mean, like, they've got to be reciprocal in this sense. All right? So what does this all mean? Sadness. There's so many more things to tell you guys. So let me tell you where we're going. This basically is opening the box for us to derive all of the inverse function derivatives from Calculus 1 the same way we did before. So like we'll prove the power rule. The derivative of z to the power p is p z to the p minus 1. We can prove that. We'll be going back to all that branch stuff that we did with the logarithm. We'll be looking at how to do calculus for all those functions, like the square root function, cube root function, all that stuff. And then the other thing we're going to be simultaneously doing is, well, maybe not simultaneously, but at some point soon we'll learn about harmonic conjugates, which is the kind of deeper, interesting thing here, which is that every component function of these complex differentiable functions, they are separately solution to what's called Laplace's equation. Laplace's equation is what the voltage function has to satisfy in the absence of charge, right? So like the Laplacian equal to 0. Every component function of a complex differentiable function is a Laplace equation solution. So we'll learn how to patch together complex functions by finding what's called harmonic conjugates. And yeah, so. But this question you asked today was really good because that conformality is another really important characterization of what it means to be complex differentiable. And it's special, right? Not all functions are like that. That's actually pretty special.